Today, we're going to talk about circular motion. Which I hope you realize, unless you've been totally ignoring me for the past several minutes, or unless you weren't in class the day that we covered this. So, circular motion. Well, basically, motion of an object that's going in a perfect circle. So there's a lot of not perfect real world applicability here, because it does. We know how orbits in space aren't necessarily perfect circles. Often we can't really achieve circular motion in a real good constant manner, constant rate, all that good stuff. But at its essence, we're talking about the situation. And if you were in class today, we did an example sort of already, where there's the easiest thing to think about is someone standing in a spot. This is a person from the top down, and they're holding a string connected to some object, and they're swinging that object around in a circle. So the object's path is something like this. That's not a perfect circle, but you get the idea. It's pretty close. Okay? Well, let's assume that we're able to, or the person doing this is able to spin the object around at a constant velocity. Well, what if we wanted to be able to calculate the velocity of the object? What would we need to do? Well, let's think about what we know, or what we can measure. Well, if we're spinning an object around on a string or a rope, we ought to know the length of the rope, which would be the radius of the circle, right? If we're spinning around, the length of the rope or the string would be the radius of the circle. Well, what else could we measure pretty easily? Well, if we have a pretty good eye and quick reflexes, we could, someone could stand right here, and their eyeball could look directly at the object, and as the person's spinning, they could hit it when it goes around once, and they could hit it when it goes around again, and that would give you the amount of time it took to go all the way around the circle. And so we call that t. Sometimes that's given by, sometimes instead of time, when we talk about how long it takes for something to go all the way around, or down and back, or here and there, sometimes when it's like repeated motion like this, especially circular motion, it's called periodic motion. And sometimes instead of time, we'll call this the period of the motion, how frequently it does it, how many seconds per go round, as it were. So time and radius are two things that we could become aware of pretty quickly. Well, how's velocity typically defined? Velocity is typically defined as change in distance over change in time. Well, this should be easy then, because change in time, well, the period ought to be the change in time. So for this situation, we could say the velocity is just something over just the period, or the time it takes to go all the way around. Well, we would want the distance all the way around. Well, how can we figure out the distance from here and then all the way around back to there? Well, that's just the circumference of the circle, and hopefully from geometry remember that c equals 2 pi r. So instead of the change in distance, we can just write 2 pi r over t. So for circular motion, doesn't matter what we know, for circular motion, the velocity equals 2 times pi times the radius divided by t. And why? Because the distance is 2 pi r, and the time, change in time, is just the time it takes to go around, which is sometimes called the period. Pretty simple idea here. You just took the basic velocity formula and then talked about what's happening when it's a circle. So I'm going to do a real fast example. So here's our example. Or maybe here's our example. I don't know what happened there. Actually, I do. Imagine that there's a guy here, and he has a 4-meter rope, and on the end of the rope he has I don't know, a watermelon. So there's a watermelon on the end of a rope. Maybe this is a Gallagher, who knows. Anyway, and he's swinging the watermelon around in a circle so that the watermelon goes around the circle every 2 seconds. So it goes around every 2 seconds. We want to know the velocity. Well, this is easy, right? Because we just said the velocity is 2 pi r over t. So we just simply plug in 2 times 3.14 times 4 over 2. So we end up with 4 times 3.14, which is going to be what? 42. No. 14 times 4. 12.96 meters per second. Simple thing. If they had given you the velocity and the radius and asked for seconds, you just rearrange the formula. You know, I think I've got you guys trained pretty well to where you don't need your hand held too much on this type. You know, this is just a new formula to kind of file away to use in the future. So I'm going to move on. So next, I'm going to try to recap what we talked about together in class just a little while ago. When we have a situation like we've been talking about where we've got some, like a person and some object on the end of a rope, and the object is going around in a circle. Man, I can't draw. But anyway, actually that's not too bad. I'm just going around in a circle. You know, you may at first want to assume that there's some outward force on the object. And that makes good sense, because it seems like the object wants to fly away from you, straight out. But if you think about it, if the motion of the object is around the circle, that means at any given time, the velocity of the object is actually tangent to the circle. So if the object's here, the velocity is this way. If the object was down here, then the velocity is this way. And so forth. We can go around like that all day long. I'll do one more example up here. If the object was here, the velocity would be like that. Okay? And that may not be initially intuitive, but it's important, because if we let go of the string or the rope or whatever it is at any given time, the object isn't going to fly. It doesn't go straight out like we may expect it to. It goes this way. That's the way that works. And that's not necessarily a an obvious result. That's not necessarily something we expect to happen. Alright, so here's where this is going to get a little bit strange. Since our object at the end of our rope is moving around the circle, that means there's a force acting on it. And we've discussed this before I let you watch the video today. So there's a force acting on it. And we may think, okay, well, if the velocity is like we see it here, we may think that the force must be this direction also. That's not right, because if there was a force that way and it was already moving that way, then it would just continue moving that way. You say that again. Forget a circle for a moment. If we have just an object, maybe it's a box, we have a box, and the box is moving at a certain velocity, 3 meters per second, and then we push it with some force, then we apply some force to it, what's it going to do? It's going to move more in that same direction. Okay? So the force here isn't in the direction of the motion, and it's not necessarily clear where the force is. Well, let me take a shot at explaining this. I'm going to do a new picture. Maybe it'll make it a little cleaner. Alright, so I'll start with my circle. That's pretty round. I'm pleased with that. We got a person in the middle, and a rope, and some object over here. Alright, so in this situation, let's say that this is our velocity vector. Okay. After it goes around a little bit, I'll make these lighter. After it goes around a little bit, now this is our velocity vector. Does that make sense? Because if assuming constant velocity for a moment here, as we go around, we went from a velocity vector that was basically straight down to a velocity vector now that is kind of down and to the left. Well, let's think about this a little bit. If actually gonna scroll down here for a little while just for some more space. We'll come back to that in a moment. So let's imagine that we have some vector, some horizontal vector, and we'll go back to that up there later. And we want that vector, after a certain amount of time, to no longer be horizontal. And maybe we want it to have the same velocity, but be in a different direction. And that's basically what's happening up here, is as we go around the circle, our velocity stays the same, but the direction changes a little bit. So let's talk about the key ideas. Pay no attention to the text at the bottom. So the key idea here. What's happening? We see these have the same length. I just went to another program real quick behind the scenes and rotated it some number of degrees. I think it was 34 degrees that I rotated it. But it doesn't really matter. Actually, it's sort of interesting. We don't care. I'll make my mind up about what we care about in a little bit. But we have this vector that is just horizontal. It has no vertical component. And, you know, let's make up a number. This is 10. We'll pretend it's the velocity, 10 meters per second. And this is still 10 meters per second. But this one is kind of down to the left. It's actually 34 degrees south of the horizontal, so I guess it would be at, what do we say, 146 degrees, 146 degrees? Okay. So it's still the same speed, but what's happened to it? Well, let's look at its components. It's got a downward component, right? And it's got a component to the right. Now, what do you notice? Oops. Actually, let me get in real close. What do you notice about its component to the right? I'll bring it way down here close. What do you see? It's not as long as the other component. Huh. And well, obviously the component down is much bigger because this component down was 0. So what has happened here? What has happened to the object that's traveling at this speed to make it change its motion? Well, what is a change in motion called? An acceleration. And how has the object accelerated? Well, the object, to go from this vector to this vector, we must have had some kind of downward push because we have a downward component of velocity now. So there must be some sort of downward acceleration. But there also must be some sort of backwards acceleration, right? Because maybe let me switch colors. This is acceleration. So there's some acceleration, and we don't know how much it is, but there's some acceleration down, but there's also got to be some acceleration backwards. Why? Because remember, this length is smaller. So it's not only is it speeding up in the y direction, because we got a y component now, it's also slowing down in the x direction. So we also have some acceleration backwards. Maybe I should have made those bigger. Oops. It's a little bit bigger. But they're still green, so they're okay. So our acceleration, our actual acceleration, is some vector off in here, the resolution of those. Well, that's a weird thing. And so going back up here, as this continues, we see that we're always accelerating kind of back and away, if that makes sense. To get from here to here, they have the same length. So looking at your components again, the components of this vector, because that was horizontal, that was just vertical approximately. The components of this vector are like this. So we see that between here and here, we see that it slowed down. It's at a lower speed this way in the y direction, and it's got a much greater speed in the x direction. So between here and here, the net acceleration was kind of off in this direction. Does that make sense? Because we're no longer going straight down. Now we're going kind of down a little, but also to the left. And so if let's apply this. Let's continue to apply this. Maybe we're way over here now. Okay, and I'll just kind of eyeball this. So now our velocity, oops, that was bad. Now our velocity is approximately here. Well, our components now are going to be, well, let me switch colors. Oops. Let me actually switch colors. Here and here. So instead of going left and down a little bit, now we're going slightly less left and up a good deal. So that means we must have been pulled between these 2 points. We must have been pulled somehow kind of this way, because we've shortened the x component, and we've increase significantly the y component. So it would kind of, actually no, it'd be more like this way. Right? Well, we can continue to apply this, but the point is that the acceleration of your object is towards the center of your circle. And that's a weird thing. And this is actually called, centripetal acceleration, meaning acceleration towards the center. And I've explained this as best I can, and hopefully our discussion in class made this pretty clear. Here's another way to think about it. Try one more time. I understand this is a strange concept, a weird idea. So I'm just going to move my drawing away. Okay. So close enough. Okay. So starting again with our circle, and same kind of situation. We got a guy or a girl or a monkey or a robot or who knows what we have. We've got a thing spinning another thing by a rope. Okay. You've done that before. Where do you feel the pull? You know, we talked about a long time ago. Probably you feel the pull this way. Well, if you have a perceived pull that way, that means what? So if it feels like you're exerting a force that way, it turns out you're actually exerting a force. You are exerting a force this way. Alright? Now, assuming this object is not made of nothing, assuming this object has a mass, if you're exerting a force on the object this way, what must you be doing to the object this way? You must be accelerating it that way. So not only is there at all times an acceleration towards the center. I probably should have drawn this arrow over here. I'll draw one over here too. There's also at all times a force exerted on the object towards the center, and that's what you feel. That's what you feel on the rope. That's the tension on the rope that you feel. It's caused by the circular motion of the object. And it's a weird thing. I agree. The forces at work here and the way the velocity and acceleration and everything is happening, it doesn't make the kind of good rational sense that we expect physics to make. Well, that some of us expect physics to make. I think some of you think physics is like some kind of magical something or other. But this is a weird thing. I've tried to explain it pretty clearly, and hopefully our discussion helped with that. So this is what's going on when we're moving something, when something's moving around a circle with a constant velocity. It's actually, because its velocity is changing, like we talked about down here with our vectors, and I've covered up some of that accidentally. But since our velocity is changing, we are actually accelerating the object towards the center because the x and the y velocities are constantly changing as we go around a circle. So we are applying acceleration, which means we're also applying something that we can call the centripetal force. Okay, so let me give you some formulas. Okay, for our situation where we got a circle and a guy and a thing, okay, it turns out that the centripetal acceleration, I always want to say centrep, but it's centrip. Centripetal acceleration is equal to v squared, so the velocity of the object squared, over the radius. That may seem like remarkably simple First, we just talked about all this crazy stuff, and I see it still down here kind of. You may not really want to believe that it really is that simple, but it is. Unfortunately, I can't really explain to you why this is true, because this is one of those things in physics that is derived by doing calculus. And this is not a calculus-based physics course, so as we move forward, there will occasionally be things that I'm going to tell you. You kind of just have to take my word for. I definitely encourage you to do further study if you're curious. If you know some calculus, look it up. I know sometimes the Khan Academy videos do the calculus and show you what's going on and where that comes from. So those of you who are interested in this or considering a career in engineering or whatnot, maybe you should go look at that if you know some calculus. But for the rest of you, here's the formula. Remember it, pretty much. So that's how we find centripetal. I have another good word that I can't say. Centripetal acceleration. If we wanted centripetal force, well, this isn't tricky at all. It's just going to be the mass times the acceleration. Right? Force equals mass times acceleration. Sometimes you'll see this formula written like this, mv squared over r. But do you see that they just took that and plugged it in there to get that? So you may see this. I don't see any purpose in trying to memorize another formula because we already know that force equals mass times acceleration, so that should be good enough. Okay, I'm going to give you one example, I suppose, but then I'm going to kind of just throw you to the wolves on this because these are not particularly advanced formulas. The formulas are really easy. What's hard is the understanding, and functionally, some of you are probably just going to have to remember what the formulas are and how to use them. But I want to do my best to give the rest of you who aren't comfortable just plugging numbers in and saying it works this way because it works this way, deal with it, an opportunity to understand understand what's going on. So a quick example. Any problems today are going to be pretty basic level, but imagine that Steve is spinning a tennis ball on the end of a rope end of a 3.0 meter rope such that it goes around every 4.3 seconds. Find the acceleration and force acting on the ball. Okay, so I'm going to draw a small scale picture here just to try to, because this is really easy. So here's my circle, kind of. And here's my guy and the tennis balls here. Okay, so we're saying it goes around every 4.3 seconds, so our time, or period, if you will, is 4.3 seconds. And then the radius is 3.0 meters. Okay. So we want the acceleration. Well, We know the formula for centripetal acceleration is v squared over t, but we don't know the velocity. Oh no! Well, but I gave you that formula also. The formula for velocity is 2 pi r over t. So we can just plug in 2 times 3.14 times 3 over 4.3. Two times 3.14 times 3 divided by 4.3. So our velocity is approximately, what did that say? 4.4. So our acceleration then will be 4.4 squared divided by time 4.3. So 4.4 times 4.4 equals divided by 4.3. And so we get about, that's what I expected, the acceleration is about 4.5 meters per second squared. Now, it also asks for the force. Well, remember, centripetal, man. So I'm not an English teacher, guys. I can't say words. Centripetal force is just equal to mass times centripetal acceleration. Well, what's the mass of a tennis ball? I don't know off the top of my head. Look it up. But you can then finish the problem. Force equals mass times acceleration. Done. Alright, now, just to talk about other possibilities here, you guys really ought to be getting better at problem solving. What if I gave you the force, centripetal force, and asked for, maybe I gave you the centripetal force, the mass, and the time, and asked for the length of the rope? Well, you should be able to do that, because if you know the force and the mass, you can find the acceleration, and if you know the time, you can find the velocity, and if you know the velocity, you can find the length of the rope. Okay, what if I'd given you, the time, the length of the rope, and the force, and asked for the mass? Well, if I gave you the time, the length of the rope, and the force, and asked for the mass, well, with time and length of the rope, you can solve for velocity, which means you can solve for acceleration, and then which means you can solve for mass. So on problems like this, and I'm not sure how advanced I'm going to get with you here, but you just, like on all of them, you look at your knowns, find your unknowns, and think about it. These are, I boxed them in pink. These are your only 3 equations. Well, let me not say that. But these are your 3 basic equations that you're going to be using on all of these problems. So good luck.